So in a couple of different contexts now, we've considered the problem of choosing some number of things out of a bigger set. So imagine that I've got some n number of things and I want to choose k of them. And I want to talk a little bit more explicitly about this and break it down into two main kind of categories. So one thing that can happen is we do care about the order of the k things that we choose. And so this is exactly the problem of the soup schedules, right? So we've got n total soups, and we want to make a schedule for the next k days of which soups we're going to eat, okay? And we know how to solve this using the product rule, right? I have n choices of what soup to eat on the first day, and n minus 1 choices on the second day, and so on. So we get n times n minus 1 times dot 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 all the way down to n minus k plus 1. You should convince yourself that we really do need this plus 1 if we want exactly k things. I mean, I guess think about the fact that the second thing has a minus 1, the third thing has a minus 2, and so the kth thing in this list is going to have a minus k plus 1. And of course we could write this more compactly by saying if we do n factorial, that's the product of all that, n minus 1 all the way down to 1, but we want to cancel out some of them. We want to cancel out anything from n minus k down, so we can write this as n factorial divided by n minus k factorial. Okay, and I think in one of the activities we did in class, someone even wrote this formula or formula very like it in the spreadsheet that we made. Okay, I think the last video I made, we considered a related problem, which is what if we don't care about the order of the things that we choose? So here in this, in the example, we were just picking which k soups we were going to eat, and we didn't care about what order they were in, just which ones we chose. And we saw that we can solve this using the division rule, right? So we can think about first choosing in order k soups and what order they're in, but then we say, well, for each choice of k soups, I can put them in k factorial different orders, and I don't care about that difference, and so I need to divide by k factorial. So by the division rule, right, it's going to be this, so n factorial divided by n minus k factorial, this whole thing divided by k factorial, right, which of course we can write as n factorial divided by k factorial times n minus k factorial. Okay, and this turns out this comes up all the time, and this is called a binomial coefficient. I'll probably talk about why that is. And it's usually written using a special notation. Write it like this. And we pronounce this n choose k, because it's the number of ways to choose k out of n things when we don't care about the order of the k things. Okay? So let's think about a couple properties that this has. We'll look at a few simple properties here, and then we'll look at some other ones in another video. So for example, one property we can say is, and for each property I want to look at, we'll see why it has this property from the formula, but then we'll also think about, from the point of view of counting things, why it makes sense that it has that property. So one thing is n choose 0 is equal to 1. So let's look at the formula. When k is 0, k factorial, so 0 factorial is 1. And then we have n minus 0, that's just n factorial. So this ends up being n factorial divided by n factorial, which is 1. And this makes sense combinatorially. So this is saying if I have n things and I choose none of them, there's only one way for me to do that. Right? There's not 0, because I can very well choose none. That's a valid thing I can do, and so I have one way to do that. So that makes sense. Here's another thing. What about n choose n? So if we look at this again, right, so if k is equal to n, this is n factorial, these cancel. This is n minus n, that's 0 factorial, so that's just 1. So again, these cancel and I get 1. This is also equal to 1. And we can make a similar observation that this makes sense, because if I have n things and I choose all of them, and I don't care about the order, there's, again, only one way for me to do that. I just get all of them. And actually, those examples suggest the fact that, notice that this is kind of symmetric. So k, and I have n minus k, and those two things add up to n. So that actually suggests the following property. So n choose k is equal to n choose n minus k. So there's this kind of symmetry going on. And we can prove that easily using this formula, right? If you replace k with n minus k, this thing just becomes n minus k, and this becomes n minus k, which is just k. I just basically the k and n minus k just switch. So those are the same, but we can also again make sense of this combinatorially. So this is saying the number of ways to choose k things out of n. So this equation, one way to think of this equation is the number of ways to choose k things out of n is the same as the number of ways to choose the n minus k things that I didn't choose. Or put another way, choosing k things out of n really means taking my n things and splitting them into two sets. K things that I do choose and n minus k things that I don't. And the number of ways to choose those has to be the same, because every way of choosing k things leaves n minus k things that I didn't choose. So in the next video, we'll actually make a table of some of these for small values of n and k, and look for some patterns and see if we can make sense of them combinatorially. And before you watch that, I actually encourage you to go see if you can do that yourself. Just make a little table of n and k and fill in some values of this and see if you notice any patterns.